In the previous lecture we looked at some of the definitions of magnetism and how we measure magnetic response of a material and some of the parameters that we usually link to a magnetic property in a material, and we also looked at some of the basic definitions that categorizes magnetic materials into different categories and how we can ascertain those magnetic properties. In continuation to the previous lecture, I would like to dwell a little bit more on the classification of the magnetic property in a material, and also I will try to attempt showing some of the group of compounds which really stand out in today's functional applications. The cartoon that I have put in this in introductory slide shows that today the magnetic materials can be used in every other applications, including toys to very sophisticated applications in avionic tubes and in recording media. So, in today's lecture I will try to take you through different classification of these magnetic materials and show some example of how these materials can be used in applications. Just to recall, the two group of compounds that we can easily categorize is based on the weak magnetic response and strong magnetic response that materials display. So, weak magnetic response, diamagnetism and paramagnetism usually talks about influence of a external field on the material, whereas in strong magnetism it is a intrinsic response of a material in itself. When we say diamagnetism, although there is a very poor response from the material point of view to a net magnetic moment, but the diamagnetism per se can be used for sophisticated applications. For example, in levitating a train, magnetically levitating a train, magnetic materials are used, and those materials has to be diamagnetic for magnetic levitation. Therefore, diamagnetism in essence is not a bad response. It is as much used and exploited like a strong ferromagnetic material. So, this is one group called weak magnetic response, and strong magnetic response comes from ferromagnetism, antiferromagnetism or ferrimagnetism. We have already seen ferrimagnetism is nothing but ferromagnetism, but then there are some antiferromagnetically aligned moments which although is present, it is compensated by a strong ferromagnetic response. Therefore, ferrimagnetism is a special case of ferromagnetism, and ferromagnetism in essence is mainly seen evidently in metals, and there are very few other compounds which can be called as a ferromagnetic material, whereas in ferrimagnetism you can actually look at examples other than metals which show ferrimagnetic response, and we will look at some of the categories in the next few slides. Also, to just group these weak and strong magnetic materials, those which are weak, the diamagnetic materials or paramagnetic materials, can be categorized from the others on two counts. One, you talk about the susceptibility value and you talk about the permeability value. Both are a good measure of whether the material is good or not in terms of its magnetic response. Usually if you look at the permeability for a diamagnetic material, it is going to be less than 1, and susceptibility is definitely less than 0, whereas paramagnetic and antiferromagnetic ones have permeability greater than 1 and susceptibility greater than 0, but for neutral materials in ideal case permeability has to be 1 and chi m has to be 0. In case of ferromagnetic and ferrimagnetic materials, your permeability is far greater than 1 and definitely the susceptibility has to be greater than 0. And what is the response between these two, or what really makes them candidly different, is the hysteresis that emerges out in the case of ferro or ferrimagnetic materials, which is absent in the case of paramagnetic materials. Therefore, there is a clear divide between these two compounds, and therefore, it is very easy to understand how a ferromagnetic material would respond against an antiferromagnetic material. Now, the main thing that governs all these three group of compounds, ferro, ferri and antiferromagnetic material, is the presence of a magnetic domain, which is not a crystallite, or it is not a structural domain that we are talking about. It is the magnetic correlation that is present within the material that makes this materials very rich in its chemistry. At temperatures above a material dependent limit, thermal vibrations lead to disalignment of the magnetic moments. The material becomes paramagnetic. Therefore, in ferro, ferri or antiferromagnetic material, we usually talk about a antiferromagnetic to paramagnetic situation, or antiferromagnetic ferromagnetic to paramagnetic situation. So, the transitions are always to a totally disordered alignment of spins to a ordered or to a antiferromagnetically ordered spin state. So, this is exactly what we see in ferro and ferrimagnetism. Usually for temperature greater than temperature less than Tc, you see a very strong magnetic response, and this is usually present in the case of metals, whereas in the case of antiferromagnetism, for temperature less than Tn, that is the Néel temperature, ferro and ferrimagnetism can occur in insulators, and this is more prevalent in some of the selected metals and also in metal oxides. So, what really is a common understanding about metal oxides, transitional metal oxides, is that they are mostly antiferromagnetic, but what you would see in today's application or in the new generation compounds, what is understood to be an antiferromagnetic compound transcends to become a very strong ferromagnet and metal, and that is the beauty of chemistry, because the substitutional chemistry or materials chemistry totally puts the landscape of transition metal oxides into a different perspective altogether, because of the ease with which we can engineer the materials. So, if you know for sure, for example, lanthanum cuprate La2CuO4, which is a antiferromagnetic oxide, you can actually make it metallic and you can make it semiconducting by just substituting with strontium at the lanthanum site. Similarly, another very important compound which I will be discussing in module 4 and 5 is lanthanum manganate, which is a perovskite, and this lanthanum manganate actually is a antiferromagnetic insulator, because in the AB plane the manganese oxygen sheets are antiferromagnetically aligned along the C axis, whereas they are ferromagnetically confined in the AB plane. But when you try to disturb this manganese oxygen manganese alignment by substituting with the strontium for lanthanum, you can actually bring about a collinear ferromagnetism, where you try to introduce a ferromagnetic exchange between neighboring manganese via oxygen 2p, and therefore a radically antiferromagnetic insulator is transformed into a ferromagnetic metal, which is a very astonishing phenomena in the case of oxides. So, when you look at metal oxides, most of them are antiferromagnetic oxides, but you can easily translate them into ferromagnetic oxides and thereby affect the conductivity by mere chemistry, and that is the speciality of materials chemistry in these oxides. When you look at antiferromagnetic oxides, typically the domains are like this. Each one of this is a domain in an antiferromagnetic oxide which is antiferromagnetically coupled. As a result, your chi m in that case is going to be nearly 0, whereas your permeability is going to be approximately 1, and there is full compensation of the magnetization by the antiferromagnetic alignment. And in such a situation, in compounds like manganese oxide, iron oxide, cobalt oxide or nickel oxide, if you allow the external field to go through these oxides, you would see a situation like this where there is no influence of the flux on the system. So, this is typical of antiferromagnetic oxide, because the antiferromagnetic coupling is so strong that it cannot be removed by an external magnetic field. So, if you have a domain structure like this, the antiferromagnetic strength is of much higher order that it cannot easily be removed by an external force, and that is exactly what you see here. But if there is a antiferromagnetic interactions coming due to some impurity effect or defect effect, which is not intrinsic but it is an extrinsic factor, then even with a little of external field strength, it is possible to remove those antiferromagnetic coupling. If possible, we will deal with this in the next lecture. One of the most important or well studied antiferromagnetic oxide is manganese oxide, and if you closely look at the manganese atom, these are the oxygen atoms and these are your manganese atoms. Now, if you look at every alternate manganese atom, you would see that they are antiparallelly aligned. In any direction they are antiparallelly aligned, whereas if you actually look at the 1-1-1 plane, then all the manganese are ferromagnetically aligned. But in essence, this is an antiferromagnetic coupling, mainly because the electron here, which is actually exchanging through the 2p orbital of oxygen to the neighboring oxygen to the neighboring manganese site, is antiferromagnetically coupled, and this cannot be removed because this is a super exchange coupling which is dynamic via the 2p orbitals of oxygen, and this cannot be removed at all. Therefore, this is a very classic example of antiferromagnet. In this case, the spin orientation is due to the 3d electrons of manganese 2 plus and 2p electrons of oxygen 2, which is antiferromagnetically aligned to the T2g orbitals of manganese 2 plus of the neighboring atom. Partial overlapping of 3d and 2p orbitals result in antiparallel alignment, and this is actually dictated by the Hund's coupling or Hund's rule. Now, in that situation, if it is an antiferromagnetic oxide, you would see a chi versus T plot to show something similar to this, where you have almost a linear dependency in this higher temperature scale, but at Néel temperature the chi starts falling down. So, your susceptibility drastically falls down at the Néel temperature. Typically, this should have actually increased in this fashion, but for a antiferromagnet you would see this sort of a crossover, and this is a very important signal for antiferromagnetic oxide, and this is exactly what you see in this curve here, that all these manganese are aligned antiferromagnetically, and they are mediated via this oxygen sites. and in such case the magnetic susceptibility is not governed by Curie law, rather it is governed by Curie-Weiss law, which is dictated by this expression chi m. Therefore, for antiferromagnetic oxides your chi m will actually be related via Curie-Weiss law. Now when you come to ferrimagnetism, as we have already seen, the partial compensation of the moments actually results in a net magnetization in this form, and as a result each domain actually contributes to a net magnetization, and this is possible only in metal oxides or any metals which are partially filled, and it also depends on the crystal structure, which we will see in some of the examples. What is the behavior of this ferrimagnetic one? The permeability will be much stronger, and your molar susceptibility will be greater than 0. And if you look at the impact of the external flux line to this ferrimagnetic compounds, you would see that there is a strong correlation, or there is a interaction with the external field strength, and as a result the domain will start getting influenced by the external magnetic field. A classic example of a ferrimagnet is Ab2O4 type of metal oxides, which is called as spinel metal oxides. Spinel compounds, usually ferrites, show a very good response for ferrimagnetism, and this is the unit cell for Ab2O4 type of oxide, where you have the A cations sitting in the tetrahedral sites, and you have the B cation sitting in octahedral sites. In such case you can actually generate a variety of spinel compounds. This is a classic spinel, which is a naturally occurring mineral, and we can actually try to make ferrites of this formula, where you can have A site occupied by divalent metal oxides and metal ions, and B site by trivalent metal ions. For ferrites, B is always iron, and you can generate magnesium ferrite, manganese ferrite, cobalt, nickel or zinc ferrite. The well known spinel is inverse spinel, that is iron oxide or magnetite, where if you look at the occupation of these sites, you would see that these two ions are actually in B site, and your Fe3 plus is actually in A site. So because you have a mixed valency of both Fe2 plus and Fe3 plus in B site, this is actually called as a inverse spinel. Otherwise, in a normal spinel phase of ferrite, you will actually have always Fe3 plus in B site and M2 plus in A site. So you would see this discrepancy in most of the ferrites. The occupation of the iron atoms sometimes will be between A and B site. So this categorizes a group of compounds like ferrites, where ferrimagnetism is very much operative. And in such cases you can actually try to substitute with chromium. If it is chromium, then we can still get a cubic ferrite which is magnetic. Suppose we substitute aluminum in the place of iron, then it becomes a non-magnetic ferrite. Similarly, a non-magnetic ferrite you will get if it is if the A site is substituted with zinc, magnesium or barium, whereas you get a magnetic ferrite if it is manganese 2 plus, nickel 2 plus, cobalt 2 plus and Fe2 plus. Some of the diamagnetic materials and paramagnetic materials are listed here, and this also tells why we use those materials for applications. For example, copper, gold, silicon, silver and zinc, these are very candid diamagnetic materials, and when we look at the AC susceptibility or susceptibility chi value, you will always understand that the susceptibility will be of the order of 10 power minus 5, whereas in the case of ferromagnetic materials this will be of the order of minus 1 or it would be positive. So, the chi value should exactly tell you what sort of a material you are talking about, and most of these diamagnetic materials are in this range, and also paramagnetic materials like chromium, zirconium, titanium, aluminum, all this have a very low susceptibility value, and those which are ferromagnetic, the magnetic spin moments are actually governed by the Hund's rule, and therefore it is possible for us to calculate how much of magnetic movement each of these transition metal ions can contribute, and this is measured in terms of Bohr magneton. When we come to the range of compounds, we usually have an idea that magnetic materials are meant only for some sort of a magnetic force applications, like stickers or magnets for isolating some magnetic materials. And in today's application, most of the time we encounter only permanent magnets used in household applications, but what we forget or what might slip out of our attention is that the magnetic materials form a very solid application core, and they are used in coils, in transformers, in transducers, and not only that in power electronics, but also it finds a very important application in magnetic storage applications. So, a range of applications are there for magnetic materials. I will basically make a division between two types of materials before I show some of the applications. One, soft magnetic materials, and the other one, permanent magnetic materials or hard magnetic materials. Soft, those which show magnetic materials on application of an external magnetic field. Permanent or hard magnetic materials are those inherently have a magnetic moment. You can kill the magnetic response only by applying a magnetic field. So, with this minimum distinction, let me just take you through some of the functional applications that the magnetic materials hold. Magnets function as transducers, transforming energy from one form to the other without any permanent loss of their own energy. And for example, permanent magnets are used in a variety of applications, like they convert mechanical to mechanical energy, in other words just used for either repulsion or for attraction. So, this is one application, but you can also use the mechanical to electrical conversion of energy, as you see in generators and microphones, electrical to mechanical in motors, loudspeakers, and in charge particle deflection. We can also translate this mechanical energy into heat, for example in torque devices and in applications involving eddy currents, and more so in the recent past. Special applications have emerged out of this materials, such as magnetoresistance, Hall effect, and magnetic resonance. I will not deal with these applications precisely, because I will be talking about this when we discuss about electrical properties of materials. So, I will try to show some example on the other aspects. This is one of the cartoon that gives us some idea about what sort of materials we characterize as soft magnetic materials. These are actually a range of compounds which stands out compared to all the other known soft magnetic materials. So, I thought this would be a good way to project some of the representative soft magnetic materials. What has emerged recent past is nanocrystals, which show soft magnetic response. Amorphous alloys are traditionally soft magnetic, and ferrites are mostly soft magnetic materials, but we also have bubble memory materials which are hard ferrites. There is another group of compound called Sendest, then permalloy, which is used almost in every other applications, and then some of the alloys also show soft magnetic material compared to other alloys which are usually hard in its response. When we talk about soft magnetic materials, we need to understand they have high permeability and very low coercivity. If coercive force is very less and permeability is very high, then you can categorize that to be a soft magnetic material, which is given by mu. Mu is equal to B by H. So, B is your magnetic induction, and for obtaining soft magnetic materials there are some clues. One, material with low magnetic anisotropy, low magnetic restriction and high saturation magnetization has to be there. In the previous lecture I told you that when ferromagnetic or magnetic movements they oscillate, sometimes they can dilate and bring about magnetostriction response, and those materials cannot be a good soft magnetic material. Therefore, it has to have a low magnetostriction. And how do we get this soft magnetic materials? We can engineer it by carefully annealing with a furnace or other annealing protocols, where we try to minimize on the defect, which can help the domain valve to move easily, so that we can get this response. Another way to get a soft magnetic response is to make a ring shape, so that you can minimize on the shape anisotropy, because shape anisotropy can influence your magnetocrystalline anisotropy. As a result, if you make a ring shaped one, you can candidly minimize on the magnetic shape anisotropy. So, let me just take you through some view graphs of each of this compound, just to show why it is useful and how it is useful. Permalloy, as you would see, since we handle the floppy disk, it is important for us to understand that permalloy is a material that we use almost in everyday's practical application. As you see here, this is a 3.5 inch floppy which we no more use. We only use pen drives now with much better storage density, but permalloys are actually used in magnetic applications mostly as shield. And permalloy is nothing but a nickel iron alloy, where 20% of iron and 70 to 80% of nickel is used. Permalloy is not the other way. Usually we think that iron has to be more, but it is the other way about. 20% iron and up to 80% of nickel is there. And what is important about this, it has largest permeability, as you can see here, and it is soft magnetic metal. As you can see from this loop, it is a soft magnet and largest permeability. And what is the advantage? You can generate strong magnetic fields with very weak electric currents by using a electromagnetic core made of permalloy. So, you can see here, this is your permalloy ring, and using this with very small electric current, it is possible to generate or amplify the magnetic field. And not only that, we can try to block the magnetic flux from entering as a shield. It can be used, therefore, it can block the magnetic field that is coming from outside, or it can be used as a gate, where you can confine the magnetic flux to be confined to a particular place, and that is why it is used in floppies, in disk. So, permalloy is actually a very important alloy, soft magnetic alloy used in magnetic storage, but I am going to avoid this because I will be discussing this example later in module 5, where where permalloy is not only used as a magnetic shield, but it is also being used for magnetic read write applications. And these are some of the cartoons that you see here. permalloy is actually used as a magnetic shield in wide range of applications, including as a sensor in fast trains. Permalloy processing is also very unique because it is alloy, it is malleable, therefore you can make it as a roll or as a sheet in any form. You can see this sort of big rolls of permalloys can be made for functional applications, and as you can see here, these are all the permalloy applications that you see in making disc, and these are the magnetic recording heads that you would see in tape recorders. Today we do not see tape recorders or cassette players, but these are their head that will actually read and help you play the songs or lyrics that you want to hear, and permalloy is essentially the head that reads the magnetic information. So, this is one application of permalloy, and then ferrites are also used systematically in a variety of applications. As I have already touched upon, spinal ferrites are known ferromagnets, some are ferrimagnets, and mainly because of their occupancy in the B site and the way they exchange between A and B site will tell whether it is going to be a normal spinal or inverse spinal. You can make any sort of ferrite if you know how to play around with your A site combination. For example, you take manganese zinc ferrite and nickel zinc ferrite, you can candidly see how you can affect the other properties. For example, manganese ferrite have soft magnetic property, but they have very low resistivity of the order of ohm centimeter, whereas if you gamble with nickel zinc ferrite, then you get a resistivity of the order of 10 power 3, and these two ferrites are incidentally used very much in storage density applications. Manganese zinc ferrite and nickel zinc ferrite both are by choice used for different applications, because one gives you almost a metallic behavior and the other one behaves more like a insulator. And amorphous alloys are other group of compounds which show soft magnetic response, and usually amorphous alloys are fabricated by melt quenching or by vapor deposition, because you can deposit using a physical vapor deposition method at room temperature, then whatever is crystalline will actually grow as an amorphous compound, and then it is possible to characterize the magnetic behavior of an amorphous alloy. And since our course is designed more to materials chemistry, in the first module I have increasingly stressed on the use of chemical approaches to make amorphous alloys. I have discussed with you based on sonochemistry how we can make such amorphous alloys in nanoscale and how the properties changes. In one such example I have mentioned that what is usually conceived to be a magnetic compound can become a non-magnetic compound, what is considered to be a non-magnetic can transform into a magnetic compound when you reduce the size to nanoscale, and that is possible using simple chemical routes for preparing amorphous alloys. This is the materials which can be engineered as amorphous alloys are for example a transition metal with a metalloid. So you can actually make borides, phosphides, carbides, silicides, and we can also make alloys of cobalt zirconium or niobium cobalt, or we can make rare earth manganites like gadolinium cobalt or iron terbium compounds as alloys. These are usually used in thin film forms, and when we try to do a casting or melt quenching, usually these are rendered in thin film form. What is important about this amorphous alloys is that they have a very local atomic arrangement, and this is what we call it as short range order, because they are not totally disintegrated. They do have short range order, but they do not have a long range order. Usually this sort of amorphous material will have a X-ray pattern like this, where you have a hump at low angles, whereas at higher angles you do not see any reflection. So this low angle hump is a very clear indication that it is not completely glassy, but it has short range orders. So if you actually look at the pair correlation functions for such amorphous alloys, you would find out that there is a reflection or a response for the transition metalloids or for alloys which have which gives an indication that the pair correlation functions indicate small polyhedras like this of the order of say 4 to 12. They constitute a short range order. As a result, you can get a very different magnetic phenomena compared to crystalline materials. Nanocrystalline alloys, they are comprised primarily of crystalline grains having at least one dimension. One interesting thing about this nanocrystalline alloys is that they are usually considered to be a single domain size. In other words, they are lesser than a single domain magnitude, and most of this single domain particles are exchange coupled materials which can provide soft magnetism. And the way we process soft magnetic materials, especially the nanocrystalline alloys, is by sudden quenching. So quenching or by a preferred heat treatment of a amorphous alloy precursor, it is possible to get nanocrystalline alloys. For example, let us take the case of one composition before we look at the other examples. Iron copper niobium silicon boride actually has a nanocrystalline alloy of the composition alpha Fe3Si, where additives like copper is added mainly to initiate nucleation, because iron and copper are immiscible, therefore it will not form an alloy. Therefore you will get a massive nucleation which is promoted when you put some copper into it, and you can put some niobium in order to restrict the grain growth. So to get a amorphous phase, you put this as additive, but actually your compound is iron silicon. So when you have such a composition, it is possible to realize nanocrystalline alloys. One of the reasons why we look for nanocrystals when we look for soft magnetic properties is that the spins in a cluster are exchange coupled ferromagnetically, and the spins between the clusters are also exchange coupled in the range of coupling length called L, and that is what we see here in this cartoon. So these two are clusters, but the clusters have a correlation within itself and between the crystals, and both of these nanocrystals will have some amount of a grain boundary influence, and if this exchange can overcome the grain boundary influence and the exchange length, then they can be strongly coupled to the extent that they show a net magnetization. And this is a view graph which tells how the exchange correlation or exchange length can influence the net magnetization. The effective magnetic anisotropy, which is actually contributed mostly by the magnetocrystalline anisotropy, is given by this expression, where your magnetocrystalline anisotropy is actually governed by the correlation length. If it is short, then the crystalline anisotropy is going to be stronger, whereas if the correlation length is going to be larger, then your magnetocrystalline anisotropy is going to be weak. And therefore the reason for soft magnetism is coming from the grain size, which is very small, which does not influence the domain wall movement, and the cluster is made of a soft magnetic material with very small magnetostriction or almost zero magnetostriction. And the reason for soft magnetism also is due to the exchange coupling between clusters, which is larger than the magnetic anisotropy, because you are minimizing on the magnetocrystalline anisotropy if your correlation length is going to be lesser. This is another compound which is used widely. It is called Sendest. This is basically discovered by those researchers in Sendai, and this is actually a material which is peculiar because it is very brittle. Therefore, it cannot be used in any other form other than as a dust or as a powder. So, it is called as Sendest. The reason Sendest is interesting is that you have a very less magnetostriction. By the way, the composition for the Sendest varies in terms of its aluminum content, and it can vary from 5 to 15 or so, but usually silicon 10% will affect the magnetic property of your BCC ion. So, doping iron and aluminum can give you a special composition, and you can see here the magnetostriction for a Sendest is somewhere here, and it has a very high permeability for this particular composition, which is almost amounting to 20,000. Therefore, this is one compound which is actually used for reducing core loss, and what you do here is that this can be actually coated as a lamination in transformers. Therefore, it can bring down the Joule heating in copper coils. This material is for power and distribution transformers, and the heating effect can be minimized when you try to spray or laminate it with this Sendest. And this particular cartoon gives you an idea how little amount of silicon can rapidly alter some of the properties. For example, saturation magnetostriction or resistivity. You can see how the resistivity varies just with very little amount of silicon. Then the Curie temperature also varies down with the doping of silicon up to 5 to 10%. Now we will take a quick look at some of the materials which stands out as permanent magnets. Just want to highlight that the main divide between a hard magnet and a soft magnet comes basically by looking at the hysteresis loop. As you know, the hysteresis loop tells us about a unmagnetized state or a virgin state of a magnetic material. On application of a magnetic field, it gets saturated, and then when you remove or reverse the field, it loses its saturation, and this is the remnants that you get out of it, and then you can completely remove the magnetization or demagnetize when you reverse it. Therefore, your response in the second quadrant becomes very important for your permanent magnetic material. And as you would see here, a permanent magnetic material, when you try to reverse the field in the second quadrant here, whatever is happening here will tell you the nature of your magnetic material or the strength of your magnetic material. So, compared to a soft ferrite, which is here, a hard ferrite or a hard magnet will actually have a very high hysteresis and large coercivity, and therefore, this can be used as a permanent magnet. So, how does this affect, or what is the parameter that we use to ascertain for a permanent magnet? We can just look at it briefly. A permanent or a hard magnetic material is one which is having a remanence even at zero magnetic field or in the absence of magnetic field, and you need a very large field to demagnetize the material. Soft magnetic material on the other hand requires application. So, the demagnetization curve or the second quadrant of the magnetization or magnetic induction is the most preferred property that dictates a permanent magnet suitability as a magnetic device. So, when you try to magnetize a compound and try to reverse the magnetization, the second quadrant behavior is very important to measure the strength of a permanent magnet. The notable parameters that we use for judging is coercivity, or you talk about magnetic saturation, magnetization saturation, or magnetic induction saturation, B saturation, and popularly this BH max is what is used to ascertain the strength of a permanent magnet, which is called energy product. If the energy product is very high, which is a factor of B cross H, then more the energy factor, more stronger the field strength. As a result, it can be used as a magnetic material. This is the plot for a neodymium iron boride, which is a permanent magnet, and as you can see here, the width of the coercive field is very high, and this is typical of a hard magnet, and the behavior of your B versus H and M versus H usually is different, and how they respond in this second quadrant is what is important for the permanent magnet. And this is how we see a response for samarium cobalt compound. This is your M versus H, and this is your B versus H plot for a samarium cobalt, and you can see that the second quadrant is very clearly altered when you try to increase the temperature. And for example, the BR is nothing but your remanence induction in this case, or MR, that is your remanence magnetization, both changes distinctly as you increase the temperature, and you can see for B remanence it drops down by at least 2000 Oersted, and BH max is your energy product strength, and significantly it changes with temperature. That means it loses its magnetization with increase in temperature. Therefore, you can decide which sort of permanent magnet you can use for what application. So, at high temperatures, if they are going to drastically drop the energy product, then it puts limit on its application. So, you can use this permanent magnets in a variety of environment, and this is another view graph just to tell you where all these permanent magnets are used. This is the neodymium iron boride, and this is aluminum cobalt nickel called alnico. This is another permanent magnet, and these are ceramic magnets usually made of ferrites, and this is your samarium cobalt magnet, and this one is new generation magnets, which is nothing but a composite, which are called flexible magnets. Usually flexible magnets contain a polymer support where this permanent magnets can be interspersed and rendered into tapes or any other flexible shapes. So, by and large, when we think of the permanent magnets, you have borides or alnico, which is a alloy or a rare earth alloy, or ceramics. Usually these are oxides and classified as ferrites, which are used for applications. Alnico is one of the magnet which is used as a permanent magnetic material, and in these materials elongated magnetic particles are precipitated throughout the matrix during the manufacturing process, and therefore in the case of alnico, it is what is important is the shape anisotropy, and this is usually spin cast into a particular form. Therefore, the shape anisotropy is more important as far as alnico is concerned. The samarium cobaltite are preferred over borates because of the processability, but both are essentially very good materials for alloys. For applications where temperature is stable and it is just above room temperatures, samarium alloys are used, whereas borates are usually used for high temperature applications. And we have a range of applications coming from ceramic ferrites. The only permanent magnets which are used from the oxides are mostly ferrites, and specifically one particular compound is a hard ferrite, which is barium hexaferrite. How to choose permanent magnet materials? We have a range of numbers that will help you understand what sort of material that you can use. We look at the maximum energy product value, we look at the coercivity, and we also look at the machinability and the working temperature. All these 4 parameters decide what sort of compound that you want to choose. For example, flexible materials, the limitation is you cannot go more than 100, but you can actually render it into any form. Hard ferrites, you can play around up to 300, but processability, machinability is very poor that way. But if you look at the alloys and the borates, alloys you can use it in high temperature applications, whereas machinability is fairly decent and not very easy, whereas for borates it is possible for you to machine it because it is a rugged material. So, these are some of the parameters that will tell you which one to use, and alnico is one of the most popular material. I cannot run through all the data, but a preferred one is a composition which will have maximum energy product up to 7.5, and your coercive force is up to nearly 1000 Oersted. So, there are various compositions of alnico which will determine what sort of energy product that we are looking for. The compositions are aluminum, nickel, cobalt with additions of copper and titanium. As far as the ceramic magnetic materials are concerned, we have barium hexaferrite or strontium hexaferrite which does the job, and as you would see here, maximum that you can achieve in the energy product is of the order of 3.5 megagauss Oersted, and coercive forces up to 3000 can be achieved in this barium hexaferrite. Apart from barium hexaferrite, you also have strontium hexaferrite which can do the job as a permanent magnet. These magnets offer the best value when comparing the cost, because alloys are pretty much costlier, therefore ferrites are usually preferred. And one important thing about this ceramic oxides is that you can actually make very dense compact to the extent that the porosity can be minimized less than 5%. That is the essential beauty of this barium hexaferrite, and they are also highly resistive. So, this can be used for specific applications because you can sinter it to near to theoretical density. And rare earth magnets, there are 3 particular compositions which I want to touch upon. Number 1 is the cobaltite. Usually it is samarium cobalt, which is a very useful material. As you would see here in this particular view graph, the energy product keeps on increasing from 16 to 50, and you can tailor based on the composition that you are using, and the coercive forces can touch up to 10,000 Oersted if you can choose the right rare earth material. So, the first one is usually samarium cobalt based compounds, and the maximum that you can achieve is 9000 Oersted, and your energy product is up to 22 megagauss Oersted. Whereas when you go to the next batch of compounds, these are usually a transition metal and samarium based ones. Instead of cobalt samarium, if you go for samarium, iron, copper, cobalt, then you can increase on the energy product, or we can go for another batch of compounds which are usually borides. These are neodymium iron boride based compounds, and these are samarium iron based compounds. As you would see here, as you go down this list, the energy product can improve, and mostly it is the borides which take edge over samarium cobalt, and these are a range of iron chromium cobalt magnets that are available. And the next important application of this magnetic materials is in the area of magnetic storage, which I will continue in the next lecture, and also I will try to discuss what are all the magnetic phenomena that are involved when we try to look at this magnetic materials. So, in the next lecture I will give some examples of materials that are used for magnetic storage, and I will also discuss with you about some of the magnetic phenomena that happens which we can suitably minimize or enhance if we get to know what is the application that we are looking for.